student here, and I'm working on DAS in the Abyss team. No, I did my PhD in PGP, if you're interested. And so I will present this talk with Marie, which is an engineer, also in the Abyss team. And we are working closely together. That's why we decided to do this presentation with two people. So what is the Abyss project? So the idea is to take this amazing opportunity, which is a network of dark telecommunication cable, which is located offshore on in Chile. And this cable is amazing because it's underwater, it's close to the trench, and provides an amazing opportunity to have underwater observatories close to the subductions. So the project is to put as many DAS we can onto those fibers. And this was a project, and actually it's now a reality because we went there to install 3 DASs, and this is what Marie will show you.
So hello everybody. So I will show you some picture of our field trip in Chile. So we came to Chile last October for 2 weeks to install 3 DAS units to interrogate fibers. And so here on the map, you can see on the red segments, the segments that are acquiring data right now by the 3 DAS. So we have 1 DAS in Concon city, 1 and 2 DAS in La Serena. So in La Serena, 1 DAS is acquiring data on the south of the city, and the other one is recording data toward the north. And in total length of those fibers, we have around 450 kilometers long. So here you see a picture of the 2 DAS installed in La Serena. So basically what is a DAS? A DAS unit is this part on the top. It's like a big computer. And you have here a tactile interface where you can act to change parameters. And also each DAS unit is coupled with 1 server block. Inside you have several storages, so internal storages, where the data directly go during the acquisition. And to control that, you also can also put a screen and mouse to really interact with the machine. So I will talk a bit about the difficulties on the field, on the kind of DAS field that you can encounter. So, I mean, the difficulties we encountered there. So first, the first picture you see here, the server room where the DAS are installed. So it's not a typical field like classical seismology, like on the real field, let's say. Here it's really inside a little house, server house. And it's like that. The temperature is controlled, the humidity is controlled, and also everything here is paraseismic to be able to handle the quakes, the big earthquakes. And because, in fact, in this kind of rooms, all the fibers that are offshore arrive, and they dispatch internet access for everybody in the city. So it has to be very well maintained and so on. And so here you see the 2 DAS in La Serena installed in what we call rack field. And so the 2 last pictures are examples of what we encountered in the installations. So the first picture, on the first picture, you can see an engineer from GTD company. GTD is the company that provides electricity and that allow us to connect to their fiber. So here the engineer is building a bridge, like let's say cable bridge inside the house, because our cable that connects our DAS unit to the fiber going to the offshore sea was not enough, but it was too short. So they built a bridge just to put our fiber and that can be connected to the other side of the house. Everything paraseismic in like 10 minutes, it was done. And the last picture, it's a picture of the 2 GPS antennas we fixed on the roof of the house that are connected to the DAS interrogators to be synchronized with time. And as you see here, it was installed like in a day, within a day, by the engineers of GTD. So it was very, very nice to work with them. It was very efficient, and they were so nice. So it was a very good field trip. But all those things weren't planned, and so you have to very take the time to think about these things. And also, just after the installation of the 3DAS, we made a field trip, like a real field trip, let's say, in the desert with Bertrand Potin, which is working in the University of Chile. So it was to retrieve data from temporary stations on land that are here to complete the permanent on land stations next to the cable locations. So we can have a complementary material data to our data offshore. And we retrieved data in the desert. It was very nice, and we camped. We had several nights under the stars, and that was very nice. So that was the field trip. Also, one of my tasks in the group is to manage data. So the 3 DAS units are continuously recording data right now, and the sampling rate is 62.5 Hertz. The spatial sampling on the fiber is one virtual sensor every 15 meters. So over a distance interrogated length of cable of 150 kilometers for each cable. So it means for each cable more than 10,000 virtual sensors and a huge amount of data per cable. For example, so DAS data here is a 10-second file, and 10-second file is 13 megabytes. So for one day, approximately, we have to transfer from Chile to France directly 112 gigabytes. So for the project that will last 5 years, we estimate around 600 terabytes of data. So we have to be careful about the transferring data. So I made some routines to check automatically the content of the data if we have random noise or if we have gap in the data, because we can directly act on the parameters of the DAS unit remotely from here. So with an application that is called No Machine, we can directly connect to the DAS unit in Chile and see what's wrong in the acquisition, so we can change in live. So from October, so since like 4 months, or 4 months or approximately, we already had several issues in the data acquisition. Like what I said, we had several gaps. One amplifier switched off, so we had to switch it on again. Also, one of the DAS units for the server in one DAS unit failed, so we had to manage that with some buffers of data to copy and erase data at the same time. So yes, this is kind of, so this data management is a big consequence, and soon we will change to most for automatic tools, let's say, because for now everything is kind of made manually in routines. So that will be. And so we are recording data in strain rates. That's not very convenient for seismological applications that we want to do after. So Alister will present you the method to convert strain rate to velocity data.
So yeah, basically we get a lot of data in strain rates. And I would like to take a little time to talk about what this is somehow a problem. Mainly, the main thing is that in practice for seismology, we discovered that displacement is actually a better quantity than strain, or velocity is better than strain rate, let's say. And I would like to explain you a little bit why, and why we need to, why we do this conversion and how we do it. So to illustrate this, this is like a little simulation we did. This is like a small sedimentary basin. We have simulated like some P and S arrival that comes from the bottom as plane waves, and then need to travel through those sediments to reach this red part, the red line, which is representing the cable. And what you can see, for example, on the displacement field is that, well, there is a lot of reverberation, but still we can see a first arrival of the pier, which is on the top. We can see also here's S arrival, which is just a quite a nice spatial coherence. Whereas on the strain data, which is only the spatial derivative of displacement, well, things are much more scattered. We see slower waves. We don't see very well those two first arrivals that were pretty clear before. And this is due to the fact that if you look a little bit at the equations, well, meaning this differentiation of the displacement, you introduce an amplification of small wavelengths. So meaning that strain is more sensitive to short waves that travel slowly, and also showing it here, but it implies also complex directivity patterns of the instrumental response with clover-shaped pattern, things like that. So this is not what we want. This molecule, we're not that much interested into the scattering signature of the sediment, much more about what goes through it. So how could we fix this? Well, we have more or less a solution. One of us would like to go from strain to displacement. And mathematically, this is the naive way to do it, is to integrate strain along space. So if you do that, you get something we call deformation, which is this third panel. And you can see that there's something wrong into it. We have this kind of horizontal line so that appears. And this is actually due to the fact that when we do the integration, we need also some integration constant that we don't know. We need to determine it. And physically, what it means that basically what we are measuring when we integrate strain along the path is that we measure the distance, but not the absolute distance. It's the distance from the point of interest to the instrument. It's a relative distance. And if the instrument is not fixed, if the instrument moves, which is this U0 terms, then we will superimpose on all the data the motion of the instrument, which results in those horizontal lines here. So again, let's continue in being naive. How could we remove those horizontal lines? Well, basically, this additional artifact, let's say, is a space invariant feature. So we could just average on space, and hopefully we get this term. And all the wave field, which is an oscillating term, we can hope that it will basically convert to zero. So basically, we just do a simple average removal. And here we have something which is really close to the displacement at the beginning, but it's not exactly displacement, this is true displacement, because doing this mean removal, we also remove very long wavelength signal, meaning that this process works only for wavelengths which are shorter than the wavelengths of the linear segment. So this is for an ideal linear cable. What happens if there are some kinks? So this is another toy simulation where we have cables that do some zigzag. And well, I won't go into the detail, but at each change of directions, this reference changes, meaning that where we are only one way to crossing the cable, we have all new artifacts that appears at each change of directions. So the strategy will be to do this mean removal per section. Or there is like a more flexible approach, which is to do some sliding doing a sliding windows mean computation and remove this, which results in something like that, where we can remove the artifacts an estimation of displacement. So this is theory. Does it work in practice? And so yes, that's good news. This is a deployment made actually with colleagues from IPGP and from Study Firenze on the Stromboli. And we had the opportunity to deploy this cable, which is composed mainly of some rectilinear section of about 100 meters, and we put instruments along the cable. And this allowed to compare what we get from our method and compare it with the real velocity in this case along the cable. And you can see that it correlates pretty well. So this is great news. It means that using this method, we can convert strain to something that we know, velocity, which is something we use every day as a seismologist. We can reuse all tools that have been, most of the tools that have been developed for the seismology. And for example, one thing that now works out of the box is magnitude estimation. We can reuse all the magnitude scales that have been developed. So here it's an example in Italy where we had a little deployment of 1 kilometer long cable in a seismic area, and we compared magnitude we estimated with the cable with one from the local network, and it matches. And the last thing I would like to talk about is going back to what we said at the beginning, that displacement is better or velocity is better than strain or strain rate in terms of instrumental response, because displacement is more sensitive to long recurrent waveforms. So this is an example on the data we acquired in Chile for a smaller earthquake close to the cable. On the top you have strain rate, on the bottom you have displacement. And you can see that doing this conversion increases the spatial coherency and allow us, without further processing, to enhance those direct body wave that we are barely seeing on the results. And which is really interesting because this later, so here we can see 3 phases that are actually due to the effect of sediments. So before we jump into that, a little conclusion of this part. We have this tool that works nice, which converts strain rate to deformation, that allows to have a better sensitivity and make existing tools. Any questions on that part, maybe? Yes? Okay, so the coupling, that's a good question. Actually, it's not a problem in terms of integration because the only theoretical constraint that we need so that to make the integration work perfectly is the linearity of the cable. So if some part is poorly coupled, but then it's well coupled again, it will work correctly. So you will see the coupling will affect the result. You will have a lower displacement where there is lower coupling, but it won't mess up completely the integration process. Yep.
For the choice of words, I think sensibility may not be the best.
Okay.
Like the strain is more sensible, but it has higher frequency content, and basically what you are doing is removing these high frequencies. But at the end, you are using the strain to get the displacement, right? So both are sensible the same way.
Sensible in terms of
that you are removing, you are like kind of filtrating your signal.
Yes, it's a filter. It's a filter. But sensitivity, you mean how would you call it then?
Say removing the high frequency content maybe of the signal.
Yeah, it's both things. It's removing. Actually, it's not what we are removing is. It depends. When you do the integration, you're like rebalancing. So it's not frequency. It's like the wave number content. And then we need to remove the very long wavelengths that are problematic because of those artifacts. So it's a filtering, but the nice thing about that filtering is that at the end you get something which is similar to the displacement field that you would record with a seismometer. And I didn't discuss it, but Also, if you look at this picture, you can see also that it's less modular. And this is because actually the phase measurements that it was done by the instrument, the interrogator, well, the phase translates directly in terms of displacement. If you go out into the, and then the manufacturers, what they do, they differentiate it both in time and in space to get strain rates. And it's increases. If you look at the noise spectra, you have really high noise in the both in time and in the wave number. It's flattens the noise and it's increases the sensitivity to the wave number contents that interest us. Okay, part two. Let's see what this sedimentary phases that we observe. So instead of just having P and S arrival, what we see is a third arrival, which is this very faint and quite smooth arrival compared to the two following ones, which are pretty rough. And we interpret the fact that we see those three phases due to the presence of sediments in the area, 6 sediments. So what is the simple idea between this is that when you have a wave, for example, the P wave here that arrives at the bedrock sediment, you have some splitting. And the wave either is transmitted as a P wave or converted into this wave. So we call those phases PP for the P that's in P, and P is the one that arrives as a P, and it's converted to S in the sediment. So the thing is that in the sediment, the VP to VH ratio is really high. So PP keeps going quite transparently through the sediments, whereas the PS is really lower. Slower, yeah. And it's much more distorted. The waveform is much more distorted. That's why we have this PP, which is pretty smooth, and then the SS that is pretty much distorted. So this is to interpret this, we propose this really simple modeling, where basically we suppose that all the spaces that cross the sediments have a length that is more or less the thickness of the sediments, and we use one average VP and VS velocity in the sediments. And from this, you can compute, let's say, the expected time arrival as a function of what you get from regional models. So, for example, the regional models would give you this time arrival that suppose that there is only bedrock, and to get what you have with the sediment, you need to remove the time spent in this bedrock that it's not sediment and add instead this lower mass will give you this set of equations. The only thing which is interesting is to see that we have basically linear dependency with the thickness, which is pretty logical. And also one quantity which is really interesting is the time difference. It's a bit of variable between PP and PS. Because this is only related to what is happening to the sediments. So the P arrival arrive as a P and split in PPPS, and the differential time of arrivals is only a function of, it doesn't take into account all the modeling that is done in the bedrock. So in other terms, this delta T is a proxy. And this is the first thing we checked. So we picked manually 30 events that are located a little bit everywhere. And we measure this difference time of arrival in PS. And we can see that it's something which is pretty stable. So here it's like the average delta T for event coming from different directions. And with the error bars, and you can see that it's pretty stable, meaning that this modeling is probably not that bad. And so the first modeling, let's say, of the sediment, we know how much PP is delayed compared to the SPS. And we can go one step further by introducing what we call station correction, sediment correction, which is something which is very similar to station corrections. Just the parameterization is a little bit different, because if we go back a little bit to this equation, so delta T constrain more or less H. The only two parameters that we need to invert that we don't know yet is the velocities, the two VPVS velocities in sediments. So what we did is to do a joint localization of all the events. And we jointly do that for the localization, but also for these VPVS parameters. So basically what in practice we do localization, then we look for the VPVS that best allow to reduce this general loss. And then we relocate, we retry to do VPVS, and we converge to a solution that which gives us the optimal VPVS, which is shown in the figure here. And it gives us values of about 50 which is a few hundred meters per second. And from that, you can compute then the corrections that you need, which are shown here. So P correction, red, green and red, the PS and SS corrections. And you can estimate also the thickness of the sediments. And in practice, once you have the operation, you can apply it to the localization. So the first panel is if you have no corrections. The intermediate one is if you suppose that, so you use this delta T to convert S in PP, and you say, okay, PP is smooth enough, it's probably very close to the true P arrival. And the last one is complete correction with the complete modeling I introduced before. You can see that the fits improve at each steps. And when with this cable, it's almost linear. So we have some uncertainties. The solution looks a little bit like an axe of symmetry around the cable, but more or less the residual improves. And it leads to some locations at Zenbo. We don't have any ground truth to check if it's a true one, but at least the radials reduces. So yeah, conclusion. This method only requires 2 parameters to invert, and in great reduces residuals. But what we still need to apply it in a massive way is to have an automatic way to pick those phases. Because for now, we did it manually. It was a lot of work. So we're working on an automatic picker also. In the meanwhile, Marie will now show you how we can. So see, yeah, one thing is that actually the PP phase is pretty rare. We don't observe it often. So generally, we are left with the PS and SS. And Marie will show you how we can use classical tools to do tree catalogs by picking those phases automatically.
So yeah, I will present you the workflow we are currently using to generate automatic catalogs, earthquake catalogs on DAS. So first we apply on our data an automatic phase picking that we choose to be PhaseNet. We tried also earthquake transformer, but we choose PhaseNet because we found that the time of the picking was more precise with PhaseNet than with earthquake transformer that has a small delay on the picking. So what we have to give to PhaseNet as input is, so of course the data, so strain rate converted to velocity. We have to define a probability threshold for detection. Here we choose the 0.3 by trying different thresholds. And also what I want to say for people that are not familiar with PhaseNet is that we are using PhaseNet with a Python library called the SaisBench. And inside SaisBench, you have the possibility to choose several different pre-trained models. And be careful when you choose your model. I encourage you to try several things on your data to choose the best model, because it can change a lot. Like it can produce more outliers, it can produce, it can pick some noise that you don't want to have, etc. And for our data set, we found that the pre-trained model called DTing was the best. But we thought first that the trained model OBS was the best one because it's on offshore data and so on. But in fact, as you see, I don't know if you see well, but here the P waves are in blue and the S waves are in orange. And you see that somehow here the S phase, some S phase are mixed with the P phases, and also we have several outlier elsewhere. So for our data set, dating was the best. And it gives us the peak time, the phase type, P or S. So as Alister explained, we don't have the PP. The PP is picked, but as a P phase. So sometimes in one event, you can have a first P arrival that is PP, and also in blue, the PS peaked. So for localization, it's a bit tricky, but for now, we don't take it into account. And also it gives us the position on the fiber and the detection probability associated to the peak. And this first try for the catalog is made only on the cable, the DAS that is interrogating the cable on toward the north. And also, so the second step of the workflow is to apply a phase associator to this those points. So here I choose a gamma associator that is a Gaussian mixture model association, and it's an algorithm. It's a unsupervised algorithm of machine learning to cluster points together based on their phase, their time peaking, and also the amplitude of the peak. So here in the figure, you can see in black all the points picked by PhaseNet over around 18 minutes. And what we see in blue and orange are the P and S, but once they've been associated by gamma. So here we can see we have 3 events, but at first you see it was completely black points, and the gamma associated those points to 3 events. So gamma gives us a first catalog, let's say, yes, a first approach of a catalog. And for each event, we have the associated peaks, gamma score for each station, the localization given by gamma is the UTM, so it's in kilometer, but it's not a good localization because it's based on a one-layer model, so a homogeneous model, and also it gives us a gamma score, a kind of RMS equivalent. And for 36 days of data, we have around 4,700 earthquakes made by, clustered by gamma. But as you can imagine, in this cloud of points, we have several noises that can be natural or that can be instrumental, and most of the time it's instrumental noise, and those noises are clustered by gamma as events. So we have to make a kind of cleaning in the catalog to retrieve only the good events. Here you have 2 examples where we have what we call vertical noise on DAS. It's instrumental noise. In fact, you see here the vertical lines. So on the y-axis, you have distance in kilometers, and on the x-axis, you have the time. And here, this is an example where we have at the same time vertical noises and earthquakes. And here, for example, gamma clustered all those points in one event. So even inside one event, you can have false detection points. I'm applying a kind of routine to clean the data. So for example, inside an event, I discard, I search the number of identical peak time because the vertical noises are very punctual in time. So they have the same exact time. So when it exceeds 10% of the peaking in an event, I delete it. Or when 2 events are, so it arrives that sometimes one event is separated in 2 because one thing that is tricky with gamma association is that you have to indicate parameters that fit well small earthquakes that have a repartition in space of points that is very small, and also you have to those parameters has to accept big events like this one that are detected over the whole cable. So sometimes big events like that are cut in two separate events, and so I said that if they are separated less than 5 seconds, I merge them as a same event. I mean, well, there are several steps like that of cleaning that are very original to my data. It's really fitting my data, so I don't know if it will be work for all this data. But yes, once I've cleaned the catalog, we fall from 4,700 to 1,800 events like that. But I'm quasi certain that those events are relevant. And then the last step is to localize well the events and to estimate a first local magnitude. So to localize the events, I use the Baillet algorithm. That is an old algorithm that really works well and fast in seismology, so I use it for that. There are several limitations about the amount of for the number of station, number of observation we can feed to Baillet, but I tried to change the program in order to accept more stations and so on for that data. And it runs with 1D layered velocity model that we took from Marot, the studies of Marot et al. 2014. They made a kind of similar study at the time in the same zone, and they inverted a 1D velocity model that really fits our zone, so it's very nice. And also, we estimate the first magnitude with the simplest equation of Richter law. And so it's what we get from that. So here you see on the map latitude, longitude, and depth. What we see is that all the events are very concentrated around the cable because, so first, the cable is very sensitive to very small events that happen next to the cable, and they are not all seen by the on-land stations. So we have many small events next to the cable, and also we are well constrained in latitude because the cable is a straight line, and we are not well constrained in depth and longitude. So it means that we have a kind of a ball here around the cable because it's not very well constrained. So to better constrain the localization, we combine the DAS network to the on-land stations network. So we applied the same routine on the on-land stations to make a catalog and so on. And when we identified the shared events by both networks, we recompute the localization and magnitude, and we have that now. So much more events and better localized. So we see here clearly the slab of the subduction. But we are also we complete the catalog, the online catalog, by a very small event next to the cable. And in conclusion, so we installed the 3 DAS in Chile last October to begin, let's say, the Abyss project that will last 5 years. We know how to convert strain rate to velocity, so it's very convenient to apply after all the conventional seismological tools, and we know how to correct sediment delays to improve the localizations and everything. And we have now an automated workflow to make catalogs. So as you want.
So what's next? Well, the idea is now to implement this catalog routing daily. Daily routing of catalog. And we're working also actively on building this automatic feature to use this thing basically. And Then there are other works that were done by Martin on the saturation, because we discovered that that has a limited dynamic range, and it saturates quite quickly. And there is also Clara that is working on other method to invert the sediment structure, but more in the imagery perspective. So maybe we have other thoughts about it in the next session. That said, thank you very much, and if you have any questions.